Okay, guys, so for the universal gravitational problems, there's a couple things we need to know right off the rip. F sub g, gravitational force, also is equal to the weight of the object. So there's a couple ways we can solve for the gravitational force here, and that is going to be the object's mass times gravity. Now, the gravity is dependent upon where you are, what location. On Earth, gravity is at 9.8. We're using 10 for the calculations. It's just easier. One other thing you need to make sure is that you know that mass does not change. Mass does not change no matter where you go. It's going to remain constant. So if I took a bowling ball on Earth, I know what its mass is. I put it on the moon, it's the same thing. If I put it on Jupiter, Neptune, same thing. It's going to be the same. But the weight, force of gravity acting on it, is going to be different because of that guy there, G. To find the force of gravity, you can take the universal gravitational constant, 6.67 times 10 to the negative 11th, times mass of the first object, times the mass of the second object, divided by the distance between their centers squared. Now, this equation at the top, gravitational force, I took out big G here because it's a constant value. It's not going to affect anything. And then I set mass of the first object to a 1, mass of the second object to a 1, and then the distance to a 1. So when you get to certain problems, when they're saying, oh, if I doubled this or tripled this, cut this in half, multiplied this by 4 times, how is it going to wind up affecting the overall force? So we're going to take a look at the first one. You have two objects, fixed mass, so that they're separated by 3 times their original distance. So compared to the original gravitational force, we don't have an actual value, so we're not multiplying anything here. Well, not multiplying what we've solved for by the original value to get our new value. So what we're going to wind up doing is, did they tell us anything about changing a mass? No. What about the second mass? Nope, not at all. So we're literally just going to have 1 times 1 as our masses, divided by, what did they tell us is happening to the distance? Distance is on the bottom. So that 1 is going to become what? It's going to become a 3. So 3 on the bottom, but what do you have to do with the distance in the equation? You have to square it. So on top, 1 times 1 is 1. So we have 1 on top, and 3 squared is 9. So we have 1/9 of our original force. So bam, there you go. Highlight it. Ba-bam. Easy. Okay, here you have a mass. They tell you you're on Earth. They want to know what the your gravitational force is here. F sub g. Weight is equal to mass times gravity. They give you mass, gravity is 10, so you're multiplying out. Here you have a distance of 1 meter separates 2 equal size masses. Okay, great. Now they're just asking, if one of the masses is doubled, what happens to the force between them? So one of our masses up top, it doesn't matter where, we're going to make it a 2 instead of a 1. Leave the other one a 1 because they didn't tell us we're changing both of them. Then divided by the distance. Did we change the distance at all? Increase or decrease? No, so it stays a 1. D is squared in the equation. 2 times 1 is 2. Divided by 1 squared, which is just 1, which is 2, so it's 2 times greater. Where the hell's the highlight? There you go. So number 4, a space probe has a mass of 5 kilograms on the surface of the Earth. What is its mass? I underline that specifically here. When placed at a location where the gravitational acceleration is 2 meters per second squared. I even highlighted it, said trick question. Why? Well, like we said before, right in the beginning, mass doesn't change. The mass does not change. So remember my corny ass joke? All right, what's a quick way to lose weight? Go to the moon. Why? Because weight, gravitational force, is your mass times gravity. So if I want to lose weight, I would need to be in a place of less gravity. So technically what you need to do is you need to lose mass. Now, since we're taking something here that has a mass of 5 kilograms and we're just changing it to a different position, I'm still asking about mass. I didn't ask about the weight. So what should the answer be? What is the mass of this object? Well, if it's 5 kilograms on Earth, it's going to be 5 kilograms on the moon, wherever. So yeah, 4, the answer would be 5 kilograms. In 5, you're given a mass of 60 kg. You're given a weight of 12 newtons at a particular location in space. They want to know what the acceleration due to gravity is at that location. So you're solving for G. You have the force of gravity is 12 newtons. All right, your gravitational acceleration, force of gravity here, as 12 newtons. You have the mass of 60. Isolate it to get G. You're good. You're good. You're good. Planet X, twice the mass of Earth and twice the radius. So what would your weight be on that planet if on Earth you're 500 newtons? Okay, well, does this thing have mass twice the normal one? Yeah, so we're going to double that. Your mass isn't changing, so it's a 1. But this says the radius of this planet also doubles. So we have to do D on bottom, and we have to double it. So double D, and then you have to square distance. So 2 times 1 is what? Very good. 2. What the hell is 2 squared? Anyone? Anybody? Anybody at all? 6. We talk. Love it. Love the energy, guys. Crushing it. 2 squared is 4, I think. If I'm wrong, someone just better, speak up there.
4.
My man. All right. 2 over 4, which reduces to 1/2. Well, not 18 halves. 1/2. So you're going to take 1/2 times. Now, if they give you an original weight or something like that, you're going to take what your new value is multiplied by that. So I'm going to take 1/2 and I'm going to multiply that by this 500. And that, ladies and gents, equals 225. Right? 25? Is the answer 25? I mean, I don't know. Excellent. Yeah. Good. 250. Thanks for the correction. And then you're going to highlight this beast. That is our answer. Okay, I do want to do 7 as well. An imaginary star, calling it star Z, has 1/5 the radius of Earth. So guys, remember from our simulation yesterday, what happened when we took the one moon and the planet and we brought them closer together? What happened to the force? It went up. All right, it went up faster than that house in the movie Up. Now it's going to increase exponentially. Now, when they're saying 1/5, well, hold on, let's do it first time. They say the mass of this star is 1,000 times that of Earth. Okay. Now, the mass of the second object, we don't know, it didn't change. But here, the distance is 1/5 of the original. Now, when you square it like that in a fraction, 1/5, you're squaring the bottom, dude. So 25, or 1, Jesus Christ, 5 squared, 25. So it'd be like 1 dividing out by 1/25th. And that would be the same as if you basically multiplied by 25. So you're having 1,000 times 25. So you're going to have 25,000 times of the gravitational force. What the hell was the original gravitational force? Having to just be 1 Newton. So 1 times 25,000. 25,000. Big numbers. Satellite. Okay, if a satellite moves in a circular orbit, so if you just do a circle, like with your finger, and you kind of keep doing that, what is going on? Can you make that at a constant speed? Yeah, you definitely could. What about constant velocity? Nah, why? Because speed is, or velocity is speed with a what?
Direction.
Hell yeah. So if you're going in a circle, you're constantly changing direction. So you can't have a constant velocity. Acceleration, besides having an equation for it, a definition for that is a change in velocity over time. So if you're constantly changing your velocity, you're constantly changing your acceleration. And then displacement is how far you are from your original starting position. That's not going to be constant because you're going to keep moving around. All right, so you should know what then the answer is for 8. You should be able to do 9 for shizzle. Number 10, though. 10. Number 10, though. Nintendo. Ha, that was awful. Anyway, following changes indicate what factor the gravitational force increases or decreases by. For example, increases by a factor of 4, decreases by a factor of 4, blah, 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 blah. So here, letter A. Earlier in the day, I was looking through other kids' Google Docs as they were doing this on their own while we were working on it. A couple people wound up getting this wrong, so I wanted to harp on this and I want to show this. When the distance is quadrupled, where is distance in the equation? Top or bottom?
Bottom.
The bikini bottom. Yep, it's on the bottom. So what you do to that, you have to square it, and that is going to greatly affect what is good up top. Now, they didn't tell us anything about the masses, so M1, M2 don't change. So I'm legitly just going to do this. I'm going to do 1 times 1 divided by, what was D now? They wanted it to be 4. Control period, if you forgot how to do the square thing. Control period to give you the exponent function, and then control period again. That's if you're working on a Google Doc. So 1 times 1 up top is 1, and 4 squared on the bottom is 16. So it'd be 1/16 F sub G of the original force. How do you get F sub G? Or how do you get the subscript? It's control comma to get the little subscript, dude. Okay, one mass is made 5 times larger. One mass is 1/3. Okay, you guys should be able to knock that out of the pack. 11, same. You're doing the exact same thing, except, right, you do have a original weight. In this case, it's 60. So for number 11, right, or in number 10, if they told us that the original gravitational force between these objects was 60 newtons and it's 1/16 of that, you would then do 1/16 times 60, or 60 divided by 16, and then you're going to write out your final answer. So for 11, I want you to do this whole piece here, get your answer, and then multiply like that by 60, and then your final answer. All right, this one should be fine. Explains it. Explains it. And I explained that one as well. And then at the bottom as well, this is what we kind of dealt with yesterday. So I have just a couple of examples if you forgot or you just didn't actually give a crap and weren't paying attention. Not naming names, but you know who you are. And gravitational force, all right, again, we're not putting big G in here because that is a constant value. It's not going to affect our proportions. All right, so double one mass, what happens? So this one should be beneficial for you for 11. All right, guys? So that is what we're going to be doing. Please make sure you're getting started and working on